Good morning, everyone. So we're continuing with our MOOC course on distributed acoustic sensing using fiber optic cables. And today we have the pleasure of having Robin Rostadbotnen from NTNU in Trondheim. And Robin would talk about, I think, dark fiber around Svalbard. And so these lectures are recorded and it's being shared via our portal Studium, and you can grab them there. So without any further ado, I leave the floor stage to Robin.
Okay. Thanks, Alireza, and thank you for inviting me to do this lecture. So I'll be talking about the observable signals on a marine distributed acoustic sensing or distributed acoustically sensed cable from Svalbard. So I'll go through 4 different cases, focusing on different frequency ranges. So outline, I guess you've already been through the distributed acoustic sensing part, but I'll do a quick introduction to the Optodas unit, which we have been using for this work. Then I'll go into the study area, which is basically in the submarine environment and a fiber connecting Longyearbyen and Ny-Ålesund in Svalbard. So it's the opposite actually here. So I'll go from low to high frequency signals in 4 different cases: tidal period signals, ocean waves, earthquake, whales, and ships in the end. So basically how this Optodas unit work. The difference from my understanding to other units or interrogators is that it uses a frequency sweep as input to the fiber instead of a pulse, which means from my understanding that it can put more energy into the fiber and interrogate a longer stretch of the fiber. So in low loss fibers, it can go up to 170 kilometers, but in reality for standard telecom fibers, it goes to 140, 150 kilometers where it goes below the noise floor. But the noise floor is really increasing after 80 to 90 kilometers. So what we've experienced is that the signal normally, or the weaker signals disappear after roughly 95 kilometers along the fiber. I'll show you more of this later. I'll not go into the details of how this works. I assume that you've gone through that previously in the course. So study area, we're in Svalbard. It's in the North Atlantic all the way up to 78 degrees north. So we have 2 fibers connecting Longyearbyen and Ny-Ålesund. They are roughly 260 kilometers each. They are varying from a water depth of 450 meters to 70 meters, and of course up to the surface. The burial condition change along the fiber, which we'll see throughout the presentation, where green denotes buried fiber, red denotes unburied fiber. And this will help us to understand the data later. So normally we use a gauge length of 8.16 meters with a spatial sampling, half of that 4.06, so we don't miss anything over the gauge length averaging. So we can divide the studies that we've done into 3 periods. The initial period was for 1 month, where we acquire data over all of the length on both fibers. We had to use 4 interrogator units to catch all of the 100 or 260 kilometers, as we're limited to roughly 140 kilometers for each interrogator. So to do this, we placed 2 units in Longyearbyen and 2 units in Ny-Ålesund, and they are sending or recording towards each other. They're on the same fiber, but on different fiber strings. So the lasers shouldn't interfere with each other. After we finished this, we acquired for 1 month. We sent 3 of the units back to Norway and kept 1 of them recording in Ny-Ålesund. And this one has basically been recording since we started in June 2022. We went back with another unit in March this year, placed it in Longyearbyen, and we are now acquiring the whole stretch again, but for 1 fiber. So we have basically been swapping a bit between which fiber we are using, so we can get a long-term data for all of them or both of them. So then over to case one, which is tidal period signals, and now in this case we're below 0.01 hertz and way below that actually. So to start off, I'll just shortly touch upon what tides are, and especially tidal constituents. So tides are rise and fall of sea level. You probably know this. It's governed by how the celestial bodies move in relative to Earth. So if we pretend that we only have the moon, it will basically, where you align the moon with the Earth, you'll have high tide, and perpendicular to this, you have low tide. And then if we introduce the sun into this equation, you'll get a constructive interference when the moon and sun is in line with the Earth, and you'll get spring tide in this case. When the moon moves perpendicular to the sun, you'll get neap tide, which is then a lower tidal level. And how the moon and sun moves in relation to each other will affect the tidal levels. So this is basically two components that brings up all of the tides that we see. So basically the tides might seem quite simple to predict, but it's a lot of things that affects their amplitudes. You have the relative position of the sun and the moon relative to the Earth, and also the other celestial bodies. You'll be affected by the Earth's rotation, the water depth in the position that you're recording, the coastline and the continents, and you'll also be affected by wind and atmospheric pressure. So there's a lot of things going into how the tides behave. And then you can have tidal components that ranges from a few hours to several years. I think the longest period that I saw for one tidal component was 16 years. So you can stretch for a long, long time. So basically, tidal components or constituents are all components that make up the observed tides at any given location on Earth. And we're looking at how this is on Svalbard, basically. So then there are a lot of models on how the components might vary across the Earth. So if you look at Svalbard up here, you'll have mainly semi-diurnal tidal components, which is basically periods that occur twice a day. And you have a bit of mixture between the diurnal, so we might see some of the diurnal periods. You can also look into the amphidromic system for the different components. So basically, the amphidromic systems say how or which amplitudes that you can expect on the sea level rise and fall. So in Svalbard, you can see it's green, so it's roughly 50 centimeters from high tide to low tide. You also have this amphidromic system or amphidromic points where the high tide and low tide is the same. So if I then go to a diurnal wave or period, which is the K1, you can see that where these contour lines converge is where we have this amphidromic system. So for this K1, you have an amphidromic system just outside Svalbard. So that means that you will not really see this K1 tidal component, whereas this M2, which is green and has higher sea level variation, that should be observable. And then you have lists of the different periods and listed online, so you can actually see all of these periods and compare what you see in your data to the actual period of the different components. So in order to see this data, you have to do some simple signal processing, or it's basically, since you have so long time series, you need to handle the data in some way to be able to load it into the computer and plot it. So the way I did it was to load first 10 minutes of raw data, convert it to strain. Then I redefined the gauge length from 8 to 24 meters and a spatial sampling of 4 or of 12, which basically cuts the data by 4. And after this, I temporal sample it in 2 steps. First, I take the 10 minutes of data and resample it to 5 hertz. And then I concatenate it even more to time series of 1 day and resample it to 0.1 hertz. So then you have a data set that's easier to handle. And after all of this, I bandpass filter the data to better focus on the frequency ranges that has proper signatures. So then over to the data. So this is plots for the outer cable and the inner cable. So basically the outer cable is the one, if you look at Isfjorden, which is this fjord, and then the outer cable is the one most south. And then the inner cable is the northernmost. So basically the inner is the one closest to Fårlandet and yeah, other parts. Anyway, so you can also see on top here, I have color coded where it's buried and unburied. So you can see that where the red sections are, we have strong signals that has clear move outs and variations along the time axis, which is Y. On the inner cable, we have a really interesting place where you go clearly from buried cable to unburied to buried again. And then when we have this unburied part, you see that we get a high increase in amplitudes for this section. So our interpretation now is that these are tidal currents or deep water currents that brings in warm water and cold water as a function of time. And this is not really giving a strain on the fiber, but it's giving a temperature variation, which might induce temperature stretching and contraction of the fiber, and also a change in the refractive index. And it's probably the change in the refractive index that we see giving these signatures here. But we can still see that we have signals, especially in Kongsfjorden, which is the fjord outside Ny-Ålesund, where it's still unburied, but we have signals that goes up quite high off the noise floor and has amplitudes similar to the tidal current signals along this stretch here. So I'm going to zoom in on the different fjords to look a bit more in more details into those. So I think I've covered this slide, so I'll go to the next, which is the zoom in version of Kongsfjorden. So it's up here. So in addition to the TX plot, I've also plotted the change in water depth, which is basically you take the water depth to the fiber at one channel and take the difference to the next channel, and then you do it for all. And then you'll see how the water depth to the fiber varies along the fiber length. So in this section, this area here is especially interesting, where you see that the change is going negative and then positive, which means basically that the fiber is going quite rapidly down. It's a few kilometers, but it's still going quite rapidly down and then up. So we think that the reason we get this signal is that it's either not covered a lot by sediments in this area, or that it's hanging a bit loosely in the water column. So you can see more of the temperature variation that comes in and out in this particular area. And then you have some other sections like here and here, where you also see that you have this strong variation in bathymetry, and also in the start. Yeah. So then if we go to Isfjorden, which is outside Longyearbyen, a bit further south, we have the same curve plotted on top, but you can see it's much flatter, and it's not a lot of variation in the bathymetry. But you can still see signals popping up above the noise floor. Especially this one is quite strong, and it doesn't seem to be any rapid changes in the bathymetry. So we're not 100% sure why we see this particular signal here. Anyways, you can see in the start, I haven't zoomed in really, but you can see that there is a strong variation of periodic signal here. And this is basically varying as one of the tidal components, which I'll show in the next slides. We can also see that this is happening also further out, but with a lower amplitude on different positions there. But not that clear on the inner fiber. It's much clearer on the outer fiber. So I then take these basically all the waveforms recorded by the virtual channels that you see here on, like, I think it's 1 kilometer from the shore disposition, so it's in this type of turn here. And then I plot these waveforms for both the inner and outer fiber. And then you see this nice periodic signal. And if you take the FFT of all of these waveforms on both fibers, you get the frequency response as you see down here, where you have some clear peaks popping up on different frequencies on both fibers. And if we then go into the catalogs of the different tidal components, we can plot the frequencies that we can expect at the different, basically the different frequency we can expect. So that we can identify which component that we are observing. So the lowest frequency one has a period of over 25 hours, which is this O1, which is a lunar diurnal component. The strongest one is this M2, which is the principal lunar semidiurnal, which is related to the moon and how it moves around the Earth. And we can see that we see the same ones on the outer fiber. We also have M4 and M6, which is shallow water overtides of the principal lunar. So it's basically overtones of M2. This one has half the period, so roughly 6 hours, and this has 1/3 of the period, so it's 4 hours, I think. We can do the same for Ny-Ålesund. In the inner fiber, we see the same kind of periodic signatures. On the outer one, it's not as clear, but we can really see the difference between the two data sets, as this is really shallow compared to this. So you can see the M2, but the M4 and M6 is not clear anymore. And that's, we believe, because this is not really shallow waters anymore. Then we can compare all of these frequency spectrums, and then we see M2 is clear in both locations. M4 and M6 is clear in Longyearbyen. You can also see that the data from Longyearbyen has higher amplitudes, which is most likely due to the data being in shallower waters. And then we took the data from the Ny-Ålesund, focused on the frequency of the M2 mode, the 12-hour, 25-minute period, and we took a bandpass filter around it in order to plot it over 28 days. So in the background, you see the water level, how it varies with neap tide and spring tide, where spring tide is the high amplitudes, or higher water level change, neap tide is the smaller. And then you can see the strain that we observed on the dust data seems to be roughly following the same trend. It's not perfect by any means, but you can see, for example, here you have lower amplitudes, which correlates with the neap tide period. In this segment, you have higher amplitudes, which correlates with spring tide. In future work, we want to extend this to even more days and also test it for the Longyearbyen data, which has a clearer M2 mode, actually. Okay, so that was case one. So now we move a bit up in frequencies to 0.02 to 0.4 hertz, which is basically ocean waves or ocean surface gravity waves, to be precise. So we're now focusing on the data in Ny-Ålesund or Kongsfjorden, focusing on this segment going east-west and this segment going north-south. But that will be for later. In these plots, we are looking at the data in this turn in order to see how the ocean waves will change with wind direction. So in the top here, we see in particular this one, how the wind, a histogram plot of the number of hours over 1 year of data. So you have a lot of wind from east and south, a bit from the north, which is more spread, but quite little wind from the west. So if you then look at the dust data, this is calm period. Basically, this move out means that we have swell waves or waves from distant storm system coming in from the south, moving up like this. For southerly winds, it basically coincides with the calm or swell waves, and you get an amplification of the same pattern as the calm waves or calm periods. For northerly winds, we get wind direction from in this direction here, and then you see from 60 kilometers and out, which is basically down here on the north-south segment, we see a complete flip in the arrival of the waves. And then you get more, in this segment, you get more of these crossing patterns, whereas the east-west see more of the same as the southerly winds. So we can really see directly on the dust data how the wind changes. Yeah. And then for easterly winds, you get it from this direction. Then you have a lot of topography shielding the water. You don't get a lot of fetch, so you can't really build up a lot of waves. Maybe in this area, but it's pretty deep, so it's hard to observe. And then you basically go back into this southerly wind condition. So in order to do a bit more detailed analysis, we started looking at this in the FK domain. So this will then tell us more about the direction of the wave. So I indicated with arrows here where you should focus when I start toggle between southerly wind and northerly winds. But first I'll explain a bit more. So in the top row, you have the east-west segment. So it's data recorded here, and then we take the two-dimensional FFT into the FK domain of that segment. And then the bottom row is the north-south segment. So this part here. So this particular plot is for the southerly wind, and this is for the northerly wind. So if I start to toggle between it here, you can really see this one is popping up on the northerly winds, but not on the southerly winds. And that's basically what we saw when we had the complete flip in the arrival of the waves in the TX plot. So in order to compute the incident angle of the different wind conditions, we extract frequency wave number pair, basically looking for each wave number. We try to find the frequency corresponding to the high energy in order to pick this dispersion curve here related to the ocean surface gravity wave. We do it for both the southerly wind and northerly wind, and then we compare frequency by frequency the arrivals. So the logic that we've used is that the fiber or does record strain along the fiber. So you'll get a different component of the wave number vector on this segment and this segment. So basically recording kx if we define this type of coordinate system on this, and then ky on this. And then you can use this simple trigonometry to find the angle by extracting the wave number pair for both and comparing them frequency by frequency. And then we end up by the polar plots that you see here. For a calm period, we have arrivals from this southwest, basically coming in here, and some probably reflected from this island. For the southerly wind, we see the same, a bit more narrow, and with the same reflection. For northerly winds, we get this both also arrivals from the north with the same type of reflections. The reason we have this really strong directionality is that we struggle for each segment to find or see the arrivals on low wave numbers. So, which means that you won't get 0, 90, 180, and 270 degrees. But it's either way clearly showing that for southerly winds, we see waves from the south. Northerly winds, you get waves from the south, which is related to the swell waves and wind waves from the north. And then we focused a bit more on the swell waves, which is, as I mentioned, arrivals from distant storms, which is basically storms from all over the Atlantic and other places on Earth. So basically what we do here is to identify these storms by taking the spectrogram of one waveform or several waveforms and stacking them. And then we try to identify the upsweep signature in this data. And by taking their slope and the first frequency that we see in this type of upsweep, we can compute both the origin time of the wave and the great circle distance to the storm center, where the great circle distance is basically found by the slope of the wave or the swell wave. So it's easier to show it on the data. So if you focus on this rectangle, you see this type of upsweep event, where this will be the lowest frequency, and then the slope will then be basically in the middle of this. So basically what we see here is a spectrogram over 1 year, and then you see a lot of these upsweep signatures, each one corresponding to one storm. And then of course, in some of them, we might have several storms that interfere. So we have some data gaps, which is this dark blue or purple kind of areas. And then you have these areas where we have strong local storms, basically where we don't see anything. It's so much noise in the data. It's also interesting to just look at like the winter period. That's, for example, this segment here, where you have a lot of steep slopes, which means that you have a storm close to the array. Whereas in the summer, you see it's more gentle slopes, which means that you have storms further away. So we tried to summarize this in some histograms. So if you focus on this one, you can see the orange curve is the great circle distance to each storm with the arrow indicated. So in the winter, you can see that it's the great circle distance is smaller, or yeah, and then in the summer it's further away. You can also see a change in the occurrence of the different storms, where you have more storms in the winter than in the summer. Most likely because since in the summer it's further away, so you have to have stronger storms for it to propagate all the way up to Svalbard. Then we took some of these events and since we have the great circle distance, we are missing the angle of arrival up here, and that we can use the TX plots that I showed previously to find. But then we basically find a mysterious kind of pattern where it's on a straight line connecting Svalbard to Antarctica. So you can basically, the storms furthest away is down at Antarctica and even further. So it's more that's going on here, basically. So what we believe it's happening is that we have both refraction of the water wave of the coast of Svalbard, which is steering it into one direction, but you can also have refraction of the different currents that is going along the path here. So in order to get a better estimate, we need to have more recording systems. So in Svalbard, you only have one with this great circle distance. And then if you take in, for example, the recording system at Iceland, you can get another circle, and then you get two crosses, so two possible positions of the event. And then if you have one at Madeira, you can get a more accurate position of the event. And then you can discard the angle of arrival, which is probably really affected by this refraction of different coast and currents, and hopefully give us better estimates of the different storms. Okay, and then over to some earthquakes. We're then moving up to several hertz and also below 1 hertz. So the really good and great benefit of that is that you get this recording system that takes channels every second, or every at a low sample rate. So if I start it again, you can really see how this signal, but plotted as a video of RMS every timestamp. I think it's RMS over 1 second here, or 0.2 seconds actually. And now you can see the P wave propagating from the earthquake towards Longyearbyen here. And then in this case, a high amplitude is white, and then you see a slower S wave coming in. So you can plot the data either like this or like this to see better how the wave is coming in, and you don't need to do any complicated analysis to locate the event. You can already see quite clearly where it's from. But of course, to find a accurate estimate, you need to do more analysis on it. So basically, we did this by picking out 50 first break P and S wave arrivals of this event that I just showed, and used a grid search type of inversion algorithm to locate the event. And then we compared it to the earthquake catalogs in Norway, which is NORSAR and NNSN. And we found them to be basically like this. So they're equidistant to each other, almost within 17 kilometers. And you can see from our estimate that RMS residual between them is pretty low. So by just using the dust data, we can get similar locations as what they have in the catalogs. We are not able to constrain the depth, which is basically expected since the source or the earthquake is far away from our receiving array. And then we can go into the 2022 data again and look at the complete stretch of the fiber. And then we start to see a lot of interesting patterns. We can see up here the direct P wave. Then we have some kind of reflected phase in here. Haven't looked into what this phase is. Then you probably have the S and surface waves coming in here, and then you have something coming in later down there. You can also see a really interesting pattern over here where you can see if you say that this is the direct S, and then you have a type of reflected S maybe that is coming in and overtaking the S wave and basically coinciding over here. So you might actually say something about the geology maybe from this plot alone. So this is a source out here along the mid-oceanic ridge. You can also see this pattern here, which is where it's unburied, this section. So we have less coupling on the unburied part for earthquake signals. And then we have similar signatures from a source coming from the south. And then you can see how it really changes between the two, indicating the back azimuth to the event, and probably more. And then you see the same kind of phases in the data. Okay, so then over to some work done by Kit, previous PhD at NTNU, where we are looking into the resonance in the sedimentary layer in the data. So if you take the frequency or the FFT along each channel, you get this strange pattern from the background noise, which is basically from 1 to 4 hertz. And we identify this in the end to be the resonance in the sedimentary layer under the fiber. So the lower frequencies are indicating a thicker sedimentary package. So this is thicker, and this is shallower sedimentary packages. And then, for example, up here, you are going from thick to thin. And over here, there is no sediment. And this is in Ny-Ålesund, and this is the area where you go up to the shelf and it's unburied. If we then add an earthquake to the data, you can really see a strong first mode down here, but you can also start seeing second and third modes in higher frequencies. And if we pick out, in this case, the lower limit of each mode, you can actually compute the sedimentary thickness by assuming a velocity model. So this is what Kit did in this case. So he picked these lower frequencies for each mode, and then he computed a velocity, or took a velocity model and computed the sedimentary thickness. So you can then see that these lower frequencies is correlating to the thicker packages of sediments. And then here you can see that the package is thinning out as you go towards lower distances in this case. And then, of course, he did it for the complete path from Longyearbyen in this end to Ny-Ålesund in this end. And then you see the same low frequencies and thick packages in Kongsfjorden here, and also in Isfjorden over here. And then you see this thick package, but you can also see where it's thinning out, and going over to unburied, we can see that the frequency is going towards infinity. And that's basically where it's unburied, and you can't pick out these modes anymore. You also have this problem in this area where you are more than 100 kilometers away from the source or the interrogator unit, and you get this elevated noise floor here. So you can't really see much in this particular area. In the end of the earthquakes, we also record teleseismic events. So in this case, it's the earthquake from Turkey 2 years ago, I think. And then we have to look at, in this case, 30 to 40 minutes of data. You have a clear, strong P wave in front, which is higher frequency from, I think, 1 to 5 hertz. And all of this is S waves and surface waves. And these surface waves is all of these flat events. If you zoom in, you can actually find a apparent velocity of this, and it's roughly 2,000 to 3,000 meters per second. In this case, it was an event of 7.8. The hypocenter is almost 5,000 kilometers away. Since we can do some simplified calculations to find the velocity from the hypocenter to the event, or to Svalbard, and then we find these velocities down here, which is actually correlating quite well with what one can expect. Okay, then to the last case, which is whales. There's actually a lot of whales in Eastfjorden in particular. And for this case, we have frequencies from less than 10 hertz to more than 100 hertz. I'll focus on one type of whales, which is really vocalizing a lot up there, which is the fin whales. You can, in this plot over here, see their signatures in distance and time, where you get these hyperbola kind of signatures. And you can see here, it's 3 whales vocalizing, at least 3, and it's basically 2 minutes or 1 minute along the x-axis and 50 kilometers along the y-axis. So it's no way that a whale can move from here to there and there in this type of in this time span. So we have plotted with both inner and outer fiber, so you can see a lot of interesting things. You can see, for example, this is more a V type of shape, and this is more elongated in a way. And you can see also the apex signal, due to the one component sensitivity of DAS, is much wider in the outer cable, which is where the whale is the whale is furthest away from this cable and closer to this one. And the apex is smaller in this case. Anyways, this, I'm not sure if you heard the sound, but this is the sound of the whale. It's sped up 7 times in order to be audible. So we can use all of the information that we see in this plot to say that this is actually a fin whale. You can use the waveforms here, that the calls themselves is 1 second long, which is stereotypical for fin whales. You can use the spectrograms to see that there is a downsweep from 25 to 18 hertz. And then you have this small thing down here, which is a backbeat signal that is, I think, only the fin whales that is making those. So using all of this, we can, without seeing them, quite clearly say that this is a fin whale. So in addition, we got help from the University of Bergen to do a small airgun survey, both to do some local mapping, but we can also use it to ground truth our tracking. So if you want to track the whales, we want to ground truth it to something. So when they shot, we have the exact position of the exact shot position. So we can use the same methodology on the airgun shot as to track with whale or fin whales. So we did this here. So you can see the colored line is the GPS track of the ship. The black circle or gray circle is a grid search track, and the blue dot in between there is a Bayesian filter track. So we use 2 different methods to localize and track the whales, or in this case, the ship. So you can see that there is falling quite nicely on top of the track of the ship. So this is roughly the velocity estimate that we have, and this is the error. So the average over this, all of these positions, is roughly 100 meters. You can see there are some peaks in the error curve, which is then basically where the ship is deviating from a linear line. So the methodology that we have is a bit sensitive to things going straight, but that can be improved in later work and more sophisticated tracking softwares. So then this is the result when we tracked different whales for 5 hours. So it basically resulted in 8 different tracks labeled A to G. So you have the first whale over here going from west to east. You have B, which is going quite far from east to, going from here to there. And then this D one is really interesting because it seems to be coming from the north, turning towards the inner part of the fjord and then turning back, and then we lose track of it. So it's a lot of interesting things that we can see and do with this data. So it's different things that we observed. The detection range, if we take the source location and to the end of the channel, that's the last channel that observed any signal, we get the signals that can be detected 2.4 to 9.4 kilometers away. We also find swim speeds 1.2 to 3.9, which is consistent with previous results from vocalizing fin whales. So the Bayesian filter is giving us a lot of nice information. So you can use it based on previous calls. You can predict future calls. So it's a statistical method. So in this case, I'll start it again. So in this case, the diamonds is calls that we observe. The stars is calls where no calls. So in this case here, it stopped calling, and we are keep predicting its location, and then it starts calling again, and then we can find it based on the previous predictions that we have. You can also see now that the stars, as we move along in time and we lose the local localizations for more and more time, the error ellipse increases. So it's more and more error when we haven't seen the whale for a bit. So in future work, we want to combine this whale tracking with ship tracking. I don't think I'll show ships here today, but we can use similar methodologies to localize ships. For example, if they don't have the AAS track on, and then we can localize ship and whales at the same time, and hopefully warn ships that a whale is close by, and then they can either slow down and divert their route so they don't kill the whale. So this is how one can view the data in real time. So you take RMS of a couple of hundreds of milliseconds, and then you can really see how the whales are vocalizing and how the signal is moving out from the source. So you can basically see our locations coming up here, which is that this is one location that we find, and then you can see the signal coming out at later points, first on the inner cable and then on the outer cable. Okay, so then to the conclusion of my talk. So we can see many different signals with different frequency content. The frequency range is really huge. It's from more than 100 hertz that we have seen on some whales and some ships to less than 10 millihertz. So this is at least 7 orders of magnitude of frequency. So we have mainly looked at 8-meter gauge length. For the tidal waves, we increased it a bit, but we still wanted to keep it small. But we can do a lot here, I think. So for higher frequencies, we should probably look at lower gauge length. We have recorded some data, but we are still to analyze it, especially for whales. And then for lower frequencies, we can probably use a higher gauge length in order to see more of that. So there is a lot of next steps in this data. So one thing is more in-depth analysis of each of the observed signals that we see. It's a lot of automation that needs to be done, especially for fin and ship tracking if you want to make this kind of ship's track system. Also for earthquake detection, we can do some automatic things for localization of these, and also this storm analysis can be done more with automatic systems. Okay, so thank you for your attention, and I think we have plenty of time for questions now.
Thank you, Robin. Very interesting lecture, and I think it's the first lecture now we start seeing the examples. Yeah, thanks for round of applause. So if you have question, you may want to type it in the chat box, or you can ask for raise your hand so I can open. You can have your questions. Meanwhile, while we're waiting for questions, which I don't see coming, I can maybe ask one question or two, perhaps. The distal earthquake you had from, I think it was from Turkey, or it doesn't matter where it was. You had this event that was just below the shear wave or surface wave or whatever it was, and you speculated that this could be, I don't know if you could show it perhaps.
Yeah, I can go back.
Yeah. And I think you had it maybe at 2 instances, and my question is, do you think that this could be just simply converted wave of shear to P? And that's what maybe because
You mean this plot or
no,
this?
it was where you showed
This
one
plot.
of these, the one before this. So the one before this was here. Wherever your laser point is, it looks like at the edge there you hit mainland, and that's where your shear wave hits. And it looks like you got a very well, yeah, I'm not sure now. So because slope doesn't look, it looks slow. I thought it was very fast. But nonetheless, would you think that could be a converted wave of your surface wave to P, your shear wave to P?
Yeah, I think so, because it's it's moving towards the first S, so it should be quicker. And we have seen it for several earthquakes that this one is coming like this. And we looked at actually it was the same position, and then we computed the apparent velocity, and it's increasing if you go along the fiber. So this is a bit higher than what we see, for example, here.
That's right. Yeah. All right. Particularly since it was just hitting back from the mainland, I would guess, where the fiber stops. Then I have one more question while we're waiting. The velocity estimate you got, I think it was for the Turkey earthquake, you got a P wave of 9.9 kilometer per second. Don't you think this is too high?
Probably.
Yeah.
I don't think we did an off the envelope calculation. So we didn't use any proper ray tracing or table actually. We just took the direct distance, and then we extract or removed a bit of it since it's not moving along the surface. It's going through the Earth. So most likely, I think we've used a too long ray path for the P wave. So I think this is on too high velocity. Probably the S is also too high. But the Rayleigh is most likely more correct.
Yeah, I'm not actually. I think shear is okay to me, but P, that order would require passing through some sort of diamond structures. So
that's most likely too. You can see the S wave is actually really hard to identify. So we might be lucky that we picked it too late, and then it looks more correct.
All right, maybe we got one question now. So in the future work slide of case 2, you mentioned Madeira. So is there an active system already in place? I think, is that what you're hoping in Madeira?
Yeah, there is. Yeah, we have some down there that are willing to share some data with us. So there are some storms from last year that we'll try to do this with. So they have a system that's been recording for a couple of years, I think. Also up to us.
A very interesting question, also second one, is the thickness estimated, and I think it was the very last with the resonance. Is that the thickness above the fiber, or is the thickness that is above the hard surface?
Below, so it's from the fiber to the layer, I guess, going from sediment to bedrock.
Yeah. And maybe as a curiosity, much of the work you did, of course, the later ones are geoscience related, but the whales and all those, what did motivate you to look into those signals? I mean, tidal is also geophysics in a way, but the storms and those, the really opening up very good ground for fiber. What motivated you to look into those signals?
So the reason I think Martin, my supervisor, wanted to have the fiber in Svalbard was because of all the whales. And then we can do more on tracking them and understanding how they vocalize and if they change pattern over the years. So that was one of the motivations actually to do this work. For the ocean waves, it's basically, I can go back to... So we observed this when we looked at the live feed of the data, and then we started wondering what it was. And then we started looking at the data from this weather station. And then we saw that this always happened when it was northerly winds, and this from southerly winds. So it was basically by looking at the data, we started seeing a pattern, and then we continued working from that. And then there had been some previous publications on this, or these case of ocean surface gravity waves. And then Kit, the one who did the resonance work, he also figured out these distant storms. So then we basically extended this, since we had already 1 year of data. So then we could start looking at the seasonal trend. So it's all started, or at least for the ocean waves, from the data itself.
Could this open the ground for windmill applications, in terms of direction of winds and basically long recording of wind directions and energy?
Yeah, it takes some time for the ocean to build up, so it won't be instantaneous, but you can get a good idea of the size of or the strength of the ocean, or how big the ocean waves are, and so on. So I haven't thought about it, but maybe, yeah.
All right, you got a prize from one of the participants, so thank you very much for being part of this lecture today. Bye-bye.